Here are some examples from the Day 14 assignment where we're reviewing factoring. In this case, they want us to factor as a product of two binomials. This is a quadratic trinomial. Quadratic trinomials, if they can be factored, would show up as two binomials. This is quadratic because of the square. It's a trinomial because in simplest form, there's three terms. So what I would like to do, this is in standard form, so I know that I have an a that's out in front here in front of the x squared. I have a b, which is what's in front of the x, and then the c is the constant, right? So let's identify those three numbers. In this case, I have an a of 1, b is negative 10, and then my c, my constant, is 21. So what I would like to do is a table where I compare the values of AC. A times C, 1 times 21 is 21, and I want to compare that to the B value, which is negative 10. So I want to think of all the numbers that I can think of that multiply to give me 21 but add up to negative 10. If you look at your notes, I gave you a shortcut which says that when AC is positive and B is negative, we're looking for just two negatives. So I'm first going to come up with just the numbers I can think of that multiply to give me 21. So 1 and 21 and 3 and 7, that's the only combo. And in this case, because of this combination, I just want to make everything negative. Then to jump over to the second column, I want to add negative 1 and negative 21 gives me negative 22. Negative 3 and negative 7 gives me negative 10, where the matching combo, the one that matches what was up here, is the negative 3 and the negative 7. So once I'm done with the table, I want to go back and look at A. If A is 1, I can go straight to factored form. If not, you're supposed to group, but there's also a shortcut I can show you after that. So if A is 1 here, we can go straight to factored form. Here's two parentheses. They're both going to be binomials. And the first term in each parenthesis is just going to be the variable, which in this case is x. And the second two terms are going to be what we found over here, which was minus 3 and minus 7. If you ever want to check your work, you can go backwards. The opposite of factoring is simplifying. If you were to simplify this expression here by, in this case, foiling, you should be able to eventually get back to what you started with. So let's go ahead and enter this. X minus 3, x minus 7. And I got that one correct. Okay, the rectangle below has the area of x squared minus 6x minus 7, and they gave you that the width is x minus 7, so they want to know what the length is. So we're going to ignore the fact that they're giving us the width. That's not really important. Let's just factor this trinomial. I know that on a rectangle, the area is length times width. They just happen to give me one of them. I need to find the other. I need to find the length. But since it's length times width, length and width are just factors. Factors are numbers that you multiply to get something else. So if I can factor x squared minus 6x minus 7, one of the factors will be the width, which they've already given us, but the other one's going to be the length. In this case, A is 1, B is negative 6, and C is negative 7. So AC, 1 times negative 7 is negative 7, and then B is negative 6. The only numbers I can think of that multiply to give me 7 are 1 and 7. And in this combination, when you have both columns are negative, I want a small positive and I want a big negative. And coincidentally, 1 plus negative 7 is negative 6. Since A is 1, I can go straight to factored form. So I have x plus 1, x minus 7. I already knew that one of them was going to end up being x minus 7, but now I know the one that was missing, which was x plus 1. I shouldn't need to put parentheses here because they were asking me as a length. They weren't specifically asking me for factored form. And that's correct. Okay, here they want us to factor again, and again we have a quadratic trinomial. The difference is here that a is not 1. Before I go to factor, though, see, there's something here that stands out, and that's that out in front we have a negative. A is going to be negative. We never want to factor with a being a negative. So if you look at our factoring techniques, the first thing we look for is a greatest common factor. And even though it appears that -8, -15, and 2 do not have a common factor, any number can be divided by 1. And in this case, what I'd like to do is actually divide by -1. So I'm going to factor out this negative. I'm going to factor out a -1, which would make this now +8 squared plus 15x and a -2. All the signs would change. So that now when I do go to factor, a is going to be +8, b is going to be +15, and c is going to be -2. I multiply a times c, which is 8 times -2, which is -16. And the b is 15. I'm going to just think of all the numbers that I can think of that multiply to give me 16. I won't worry about the signs yet. 16 is 1 and 16. It's 2 and 8, and it's 4 and 4. Now, in this scenario, when you look at the shortcuts, when I have a negative AC and a positive B, I want a small negative and a big positive. All of this is in your notes. And the one that adds up to 15 is the -1 and the +16. Now, we actually have two options that we can do. First, I'll show you the more formal way, and then I'll show you a shortcut, which works. What makes me uncomfortable about the shortcut is that, frankly, I just can't explain why it works, but it just works. But let's go look at the more formal way. When a is not 1, in this case we have an a of 8, what you're supposed to do is split the middle term. Factoring and simplifying are opposites. Right now we're performing factoring, but one method of simplifying is combining like terms. Well, I want to basically decombine the like terms. That 15x came about because you can combine a -1x with a +16x. -1x is -x, +16x minus 2. If I were to combine those two, I would get +15x, but I don't want to combine them because what I wanted to do was extend this polynomial and make it 4 terms instead of 3 terms. Because now that I have 4 terms, I can group. I can look for common factors with the x squared with the -x and with the 16x and the -2. So I'll keep the negative out in front. That nothing's going to happen there. And with the 8x squared and the -x, I can factor out an x. That leaves me 8x minus 1. X times 8x minus 1 gives me 8x squared minus x. Then with the 16x and the -2, I can factor out a +2. They can both be divided by 2, and that gives me 8x minus 1. Since now these two inner parentheses are the same, that means that grouping was successful, so I can factor out the groups. The negative out in front remains a factor. Then one factor is going to be the outside terms, what I factored out, which was the x plus 2. And the last factor is going to be that matching parentheses. They had to match, and that's 8x minus 1. So that's one way of factoring. That's what I'm going to end up putting in. Another way of factoring, a shortcut, and it's up to you, I can accept either one, is to say, okay, we got this -1 and this +16, so let's go straight to factored form the same way we did when a was 1. Let's write x minus 1, and let's write x plus 16. But since, in fact, a wasn't 1, let's just let's write whatever a was in front. So I'll write an 8 and an 8. But then what you have to make sure to do is to not leave it that way. You have to check and see if any of these factors have a common factor. It needs to be divided out. You're not actually going to do anything with what you divide out, but you need to divide it out. 8x minus 1 has nothing in common, so that would stay the same. 8x plus 16, though, can be divided by 8, so you're expected to do so. And if you do that, then you get x plus 2. So in the end, the negative that you had out in front That has to stay because that was independent. That you brought that out at the beginning. And then you still have the 8x minus 1. That was still a factor. And the x plus 2. Either way, you get the exact same factors. It doesn't matter the order. You can write the x plus 2 first, or you can write the x minus 1 first. So negative x plus 2, 8x minus 1. And that's correct. Okay, let's do one more. Here, luckily, I don't have to factor out a negative, but my A is 12, my B is 17, and my C is 6. So when I make my table, A times C, 6 times 12 is 72. And I'm looking for numbers that add up to 17. So the first thing I want to do is come up with all the numbers I know that multiply to give me 72, which is going to be 1 and 72, 2 and 36, 3 and 24, 4 and 18, 6 and 12, 7, no, 8 and 9, and that's it. And in this combination, I want, when I have positive and positive, then both of my factors are positive. So I would make all of these numbers positive, 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 positive. And the one that's going to end up adding up to 17 is the last one, the 8 and the 9. Okay, you can split the middle term in group. I'll show you how that looks. 12x squared, instead of writing 17x, I'll write plus 8x plus 9x, because 8x plus 9x is 17x plus 6. If I do that, now I can go look for common factors within the groups. 12x squared and 8x have a 4x in common. You can divide them both by 4x, which leaves me 3x plus 2. 9x and 6 can both be divided by 3, which leaves me a 3x plus 2. Grouping was successful because my parentheses match. So one factor is going to be the inside, the 3x plus 2, and another one is going to be the outside, which is the 4x plus 3. That's the more formal way of doing it. That's the way you would probably see it if you were looking in a book. The other, less formal way of factoring, got to find some space here, would be to go ahead and get these factors and just say x plus 8. Also, please don't get in the habit of just always writing x. The reason why I'm writing an x is because the variable was an x. If the variable would have been a y, I would write a y. If it was a z, I would write a z. And then I'm going to write a out in front. Since a was 12, I'll write 12x and 12x. And if there's any common factors, I have to divide them out. I'm not going to do anything with them, but other than just divide. These can both be divided by 4. These can both be divided by 3. So I end up with a 3x plus 2, and I end up with a 4x plus 3. In either scenario, we ended up with the exact same thing. X plus 2, 4x plus 3. Okay, so here's another one. Now this is quadratic, but for the first time now I have two variables. Notice how one of the variables, the p, is going in descending order of exponent. Here I have a p squared. This p is to the first power, and then I don't have any p's at all. And the q is going in the opposite order. First there are no q's, then this is a q to the first, and then this is a q to the second. So the trick here is to actually ignore the one that's going in increasing order. I'm going to ignore the q's. I'm going to focus on just the p's. And if the q's weren't there, then I would have an a of 1, a b of 7, and a c that appears to be negative 18. So my first column would be negative 18, my second would be 7. All the numbers I can think of that multiply to give me 18 are 1 and 18, 2 and 9, and 3 and 6. In this scenario, when you have a negative first column and a positive second one, I would like a small negative and a big positive. So the one that ends up working out here is the negative 2 and the positive 9. Since a is 1, I can go straight to factored form. So I will write, in this case, p minus 2, and then p plus 9. But the problem here is if I multiply p minus 2 times p plus 9, I'm not going to get what I started with. You should always be able to go backwards if you wanted to. But there's a quick fix for that. Just attach the q to the second term. So p minus 2q and p plus 9q. Okay. What's different here is look at these look at the exponents here. This is far more than quadratic. Here I have an 8th degree, a 4th degree, and then I have a constant. So the ways that we know how to factor are not supposed to work on 8th degree polynomials, but in this case, because of the way that it's laid out, we can actually get away with it, because really x to the 8th is the same thing as saying x to the 4th squared. So when I substitute, instead of plugging in an x, I'm going to plug in an x to the 4th. You know, x to the 4th is just x to the 4th. So I can treat it as if it was quadratic, because they're going down in even increments, 8th degree, 4th degree, and then constant. So I'll treat my a as 1, b is -8, and c is +12. So I'm looking for multiply to 12, give me -8, 1, 12, 2, 6, and 3, 4. In this scenario, everything is supposed to be negative, so the one I want is the -2 and the -6. So I would write x minus 2 and x minus 6. But if I multiply x minus 2 times x minus 6, I'm not going to get what I started with. But remember what I told you the fix was going to be. In order to treat this quadratic, it's the same thing as saying the first term is x to the 4th squared. So that's what I want to plug in over here. Instead of plugging in an x, I'll plug in an x to the 4th. Now, if you were to FOIL that, you would get what you started with. So let's write x power 4 minus 2 x power 4 minus 6. We'll do one more here. This is a 4th degree, which is also not supposed to work within the factoring methods that we know, but this one here, this polynomial has a common factor. All of these terms can be divided by -5h squared. I want to make sure I'm dividing by a negative, because that's going to turn my first term into a positive, which is what I wanted. So when I do that, I divide each term by -5h squared. That leaves me an h squared in my first term. That's going to leave me a positive 3h with my second term, and that's going to leave me a positive 2 with the last one. If I don't want to distribute, but if I were to distribute, then I would end up with what I started with. Okay, but I want to make sure I factor completely. Look at this word, factor completely. I've already factored, but I haven't factored completely because I still have a factor that can be factored further. And that's this trinomial that's left inside this parentheses. In this case, a is 1, b is 3, and c is 2. So I'm looking for two numbers that multiply to give me 2 and add up to 3. That's pretty obvious. It's +1 and +2. That gives me 3, so I would continue to factor. I already have this factor of -5h squared, but now I'm going to have an h plus 1 and an h plus 2. Now none of these factors can be factored any further, so that's going to be my final answer. -5h squared h plus 1 times h plus 2. and that's correct. All right. Let's keep on factoring here. Here we have 4 terms. The first thing I'm looking for is a common factor. Do all of these have something in common? They do not, though. But luckily, because there are 4 terms, I can attempt to group. These first 2 appear to have an n in common, which leaves me an n plus 2. These second 2 appear to have a p in common, so I bring out a plus p. That leaves me n plus 2. Grouping has now been successful because my parentheses are the same, so my factors are going to be what's on the outside, which was an n plus p, and on the inside, n plus 2. It doesn't matter the order as long as the factors look exactly the same. I could write n plus p times n plus 2, or I can write n plus 2 times n plus p. Either one is correct. There's my n plus p, n plus 2, and that's correct. Okay, Maverick and Mac were each asked to factor the quadratic expression negative k squared plus 4k plus 21. Their responses are shown as below. Which student wrote the expression that is equivalent? Well, you could try to factor this, or in this case, the way that this is formed, you can also even try to you can also just simplify each one and see which one gives you what you started with. You can try to FOIL. I'll go the factoring route. Just because that's what we're working on. So the first thing I would do if I wanted to factor this, I would factor out the negative. I don't want to have a negative out in front. So I'd bring out the negative 1, which would leave me k squared minus now 4k minus 21. They would change signs. So my a is 1. I have an a of 1. My b is negative 4, and my c is negative 21. So I'm looking for 2 numbers that multiply to give me negative 21 and add up to negative 4. Well, the numbers I know that multiply to give me 21 are 1 and 21 and 3 and 7. And in this scenario where both columns are negative, I want a small positive and a big negative. So the one I end up keeping is the positive 3 and the negative 7. Since a became 1 due to my greatest common factor, I can go straight to factored form, a negative. Notice how I'm not writing an x, I'm writing a k plus 3, and k minus 7. So we can see that Maverick tried to do the same thing, and he factored out the negative 1, but the problem with Maverick is it looks like he messed up the signs. He has a k minus 3 and a k plus 7. If he would have had the signs correct, he would be correct. Now, Mac didn't factor out the negative 1. He has a k plus 7, which is incorrect, and he has a negative k plus 3, but we want to check and see what would happen if we were to factor this negative into either one. You can't do it into both, but if you could do it into either one. So if I were to, in this case, I would focus on the k plus 7 because that would have to change. But if I were to factor this negative into the k minus 7, I would get negative k plus 7. So there's no way that Mac can be right either. So in this case, they're both wrong. And that's correct. Okay, difference of squares. When you have 2 terms, the first thing you look for is the greatest common factor. Here I actually do have a greatest common factor. Both of these terms can be divided by 3. When I do that, I am left with, let's see, is it 4? No, not 49. 108 divided by 3 should be 36. 36 minus x squared. I have already factored, but again, I want to factor completely. So I want to make sure that the factor I have cannot be factored any further. The only other way that we know how to factor 2 terms right now is if we have a difference of 2 perfect squares. I do have a difference, a subtraction. It has to be subtraction. And so the question is, are these perfect squares? And they are. 36 is 6 squared. X squared is x squared. So now it's just factoring by formula. I'm not doing anything special. All I'm doing is substituting. If you look at your notes, it says that when you have an a squared minus a b squared, that's the same as a plus b and a minus b. So I'm going to get each of these numbers I'm squaring. On one of them I'm going to add, and on the other one I'm going to subtract. Make sure that the one that ends up changing sign is the one that came after the difference, which in this case was the x. I'll do one more. This one also has a common factor, and it also happens to be 3. If I factor out a 3, I have an x squared, and 147 divided by 3 is 49. So I'm going to keep the 3. That needs to remain a factor. I notice how I do have a difference. If that was plus 49, then I'd have to stop where I'm at. And x squared is x squared. 49 is 7 squared, so I'm going to write x plus 7 and x minus 7. It's just factoring by formula. Okay, here we have some perfect square. This looks like it might be a perfect square trinomial. You saw these last module when we were completing the square. I want to again factor completely, so the first thing I always look for is the greatest common factor. Can all these terms be divided by the same number? And it looks like they can. It looks like they can all be divided by 3. I'm going to go ahead and change the order of this. I think it might just help you out. You don't have to do this, but I'm going to write the 3x squared first, then I'll write the minus 24x, and then I'll write plus 48 to put it in standard form. And now I'll go ahead and factor that 3 out, which leaves me x squared minus 8x plus 16. So this could be factored with a chart like you saw earlier in the notes, but before I get to that, when I have 3 terms where the first and last terms are positive and perfect, both of these are positive and they're perfect squares. X squared is x squared, 16 is 4 squared. I could try to see if I can apply a shortcut. And that shortcut would be to see if this middle term is equivalent to 2, it's always going to be 2, times whatever you were squaring in the first term, which is x, times whatever you were squaring in the last term, which is 4. And 2 times x times 4 is 8x. And you might say, well, but I don't have an 8x, I have a negative 8x, and that's fine. There's a formula for both. If you look at the notes, the middle term, it does not matter the sign. So the formula for factoring a perfect square trinomial is 1 parentheses with a square on the outside. In this case, I had a 3 as a GCS, so I have to write that out in front. Then I'm going to write the first term I was squaring, which was x. The last term I was squaring, which was a 4, and I keep that middle sign, which was a minus. So in factored form, this should come out to be 3x minus 4, and then the square on the outside. Do one more of these. Okay, again, it looks like we happen to have a perfect, well, we don't know if we have a perfect square trinomial, but it looks like we have a common factor. All of these can be divided by 8. So if I factor out this 8, I'm going to have an x squared. 112 divided by 8 is 14, so plus 14x. And then 392 divided by 8, that should be 49. Okay, so I could try to do a factor chart if I want to, or I can see, well, hey, look, first and last are positive and perfect, and then the middle term, check to see, is it's going to be 2 times what I'm squaring first, which is an x, what I'm squaring at the end, which is a 7, and that does give you 14x. It does match the middle. So in factored form, I'm going to have the 8 that I had on the outside already, 1 parentheses with a square on the outside, borrow the sign in the middle, then what you're squaring first, and then what you're squaring last. These numbers get substituted into the formula. And here with the this is kind of a mix of where you might get some higher degrees, but it looks like from the heading that we're going to have special products. So these could be potentially perfect square trinomials or difference of squares. So let's see. First thing I look for is a common factor. It does not appear that I have one. Okay, but if I look, my first and last terms are positive and perfect. And in this case, they're positive, but they're also perfect. Like 121c to the fourth is really just 11c squared squared. If I multiply 11c squared times itself, I get 121c to the fourth. Obviously, 4 is just 2 squared, so let's do our test. Let's check for a perfect square trinomial. 2 times 11c squared times 2 gives me a 2 times 11 is 22, times 2 is 44, c squared. Since that does match the middle, I do have a perfect square trinomial. I'm just going to have one parentheses with a square on the outside. I'll borrow the sign in the middle, which was a minus. In this case, since I didn't have a greatest common factor, nothing goes out in front. And then I'll just substitute 11c squared and a minus 2. Now, you do have a minus. You have a square, so you want to make sure that none of your factors can be factored any further. But since what's on the inside is not a difference of squares, that cannot be factored any further. So we are done. 11c squared minus 2, and then don't forget the square on the outside. We'll do one more, unless they throw in a difference of squares. But let's see here. I'm looking for a common factor. I don't have one, but the first and last terms are positive and perfect. This is 3m times 3m is 3m squared, and this is 5n squared. So let's check. Let's do the test. 2 times 3m times 5n. 2 times 3 is 6, times 5 is 30, mn. That does match the middle, so I have a perfect square trinomial. One parenthesis, square on the outside, borrow the sign in the middle, and then now just substitute a 3m and a 5n. All right, see, they do have a difference of squares here, so we'll have this one be the last one. Okay, here I have two terms. I have a difference, but it doesn't appear to be a difference of squares. I would still look for a greatest common factor first, but I don't have one. Now, 16x to the 6 is really the same thing as saying 4x to the third squared. If I multiply 4x to the third times 4x to the third, I would get 16x to the sixth. 81 is just 9 squared. So indeed, I do have a difference of squares. Nothing else much to check. This one is just pure substitution. 4x to the third, one of them is going to be plus 9. And the other one is going to be 4x to the third minus 9. Eventually, we'll learn a way to possibly continue factoring these to what are called sum and difference of cubes. Even if we could, these aren't a sum or a difference of cubes, but it is possible to factor cubic binomials further sometimes, just not in this case.